derive the equation of integrator circuit, Opamp integrator. So in this session, we are going to see about how we can derive the equation of Opamp differentiator. Okay. So likewise, we can say that. So like how the integrator perform the integration here also. So it performs the mathematical operation performs the mathematical operation of difference performs the mathematical operation of differentiation. Here also we are using. So that is we are exchanging the here the in integrator we are using the RC that is the input side we have connected the resistor and the feedback we connected the capacitor. But here just we are exchanging in the input side we are connecting in the input side we are connecting the capacitors and feedback and the feedback that we are connecting the resistor. So that is the difference we are doing. So just we can design the circuit first. So here your operation amplifier and likewise in the like integrator here also we are having one compensation resistor which has been grounded. So this will be called as the compensation resistor. I told you in the last class why we are using the compensation resistor means here to nullify the input bias current existing between the input terminals. Okay, minus plus that is the inverting and non-inverting terminal. So to nullify that effect input bias current effect we have connected the compensation resistor. Thus, I have mentioned the compensation resistor is nothing but it is equal to the input. It is equal to the feedback resistance. Just it is equal to the feedback resistance. Okay. Here, so here I am connecting this capacitor. Here I am connecting capacitor C1. Just I am connecting capacitor C1. Then we are connected resistor. In the feedback path, we have connected the resistor in the feedback, the output of the now. Here I am connecting the input voltage VA. So I am connecting the input voltage VA and applying to the inverting terminal. Okay, now we can have so likewise here this resistor, this non-inverting terminal has been connected to the ground. Since it is connected to the ground, so the voltage at this node will be 0 volt. This node will be 0 volt. So if the node is 0 volt, due to the threshold ground effect, this node also will be 0 volt. For example, I am taking this considering X, the node X. So at node X, so node X is 0 volt. Node X will be 0. So at this node, voltage will be 0. So I can say Vx, that is a Vx equal to 0 volt. So Vx equal to 0. Okay. Now, so usually, so the current will flow from higher potential to lower potential. So here we are having a 0 volt. The current flow will be here. So what is the current flow here? Just I'm considering this will be the high voltage current. Okay. This I'm considering this is the 3x. This is 3. This is 3. Okay. Now current entering. So let's apply the current equation. So current entering the node will be equal to the current leaving the node. And current leaving the node, so I want to use due to the high value of resistance, which is 100 between the input and the input terminals, then the resistance value will be very much high. So due to that effect, there will be no current flow. So there will be no current flow. So I can write here I1 plus IF is equal to. So there will be no current flow. So 0. So this is the current equation. Now expand the I1 and IF. How will you write I1? I told you that is the Q is equal to CB. So that is the electric charge stored in the capacitor. So that is the flow of rate of charge. The flow of rate of charge will be called as the flow of rate of charge will be called as the current. It is called as the current. It will be C into dV by dt. So this is the usual formula. And flowing through the capacitor. So we can take the current flowing through the capacitor will be C into dV by dt. So here I can write, how we write? So here C1 into, so what is the voltage? That is the VA minus VS. VA minus VS divided by V into VA minus VS divided by dt. Okay. So C1 into derivative of Vn minus Vs divided by Vt plus I1, that is the IF. How I can write IF? So here also I'm flowing from higher potential to lower potential. So V0 to V, that is a Vx. So here V0 minus Vx divided by R. That is that. This is feedback is to R. R is equal to 0. Okay, now, so we know that Vx equal to, so due to the lecture law, Vx equal to 0. So apply the 0 term, so C1 into d Va by dt plus Vx into 0, V0 divided by R. V0 divided by R is equal to 0. Okay. So we actually need V naught. That is the output equation. The output equation. So we can maintain V naught divided by R is equal to minus C1 into T V by D minus C1 into dV. Actually, you need that V naught is equal to, finally we can write V naught is equal to minus RF into C1 into dVi by dt. So that is the RC will be the constant here. RC is constant. So that is actually what is the output in here is, so that is the derivative of the input. So this is the dV dt. So that is the output will be the derivative of the input in times of the, so that is RF and C1 times. So the derivative of the input. This is the output. Here we know that. So what is the meaning here? Since we have connected the input, that is the input voltage through the inverting terminal, so it will look similar to the inverting operation amplifier. It looks like an inverting operation. It is working on the mode of the inverting operation amplifier. So here we are having a 180-degree phase. So then here 180-degree phase. Okay. So this is a complete output equation of differentiator, Opamp differentiator. We can know that simply we can, for the output, we can have a waveform. So for example, I'm giving square waveform. If I'm giving square waveform as an input, then I can have the output value the height or positive signal. So since it is a inverting, it is working on the inverting mode. Here the output will be the value is 5 feet and the energy. Here value is 5. Value is 5 here. Then value here 5. Then done. So here do it work. So the output will be the spiral wave. The in the form of spiral wave. So this is the this is your input here. This is your output here. So output will utilize in the spice form. So this is the complete operation of the Opamp differentiator. So first what we have seen, we know that our output will be the differential. That is the differential of input voltage while we are applied through the inverting terminal. Okay, VA. Then we have connected to the capacitor has been connected to the inverting terminal. Then your RF, that is the feedback ratio, which has been connected at the output terminal. Here. Then for non-working terminal, so usually, so likewise in the integrated we can say, we have connected a compensation to the non-working terminal, which is equal to the RF. Here, why they are using this compensation units to nullify the bias current existing between the input terminals. Okay. And due to the virtual ground, we know that Vx equals 0 volt. So by applying the current equation, I1 plus I is equal to 0. So making this, we have finally we have got that V0 is equal to minus R into C1 into dV. That is the derivative of the input voltage. This symbol we know that the negative. Since we are having this working on the inverting mode, we are having the 180-degree phase shift. So that is the wherever we are having a positive signal, there will be a spike in the at the output down. So that is a negative output. Clear. So this is the complete operation of Opamp differentiator. Thank you.